go.
All right, hello everyone. Today we're going to do a lesson on thermal energy. So if you're with me on the PowerPoint slide, let's go on to slide 2. We're going to start with the idea of particle motion. Now, we all know that all matter is made of particles. For example, we all know about a water molecule. We know the formula for water is H2O. Now what that means, of course, is that a water molecule has 2 hydrogen atoms and 1 oxygen atom. Now, we also know that these water molecules in a glass of water, they're not just standing there. They are constantly moving around. So this motion of particles, this movement of particles, is the source of thermal energy. Let's take a look at the slide. You'll see in point A, particles moving fast will have heat and vice versa. What this means is that if I take that glass of water and I put it on the oven or I put it in the microwave so that the water becomes hot, the water molecules will be moving very quickly. And as that water gets colder, the water molecules will move slower and slower. So when matter is hot, the particles, the molecules, move very quickly, and when matter is cold, the particles move very slowly. Now, we also know that at 0 degrees Celsius, water will freeze into a solid, just like stone or the wood of this table. However, just because a matter is solid does not mean that the particles have stopped moving. Even in solid matter, the particles are still moving. Now, as that solid gets colder and colder, the particles will move slower and slower and slower until they finally stop at a temperature which we call absolute zero, negative 273 Celsius. That's 0 degrees Kelvin. And that's when particles stop moving completely. They have 0 potential and 0 kinetic energy at all. All right. And as you see in point D, the amount of motion depends on the state of matter. Obviously, in a solid, particles will only move a small amount, where in a liquid, the particles can move freely. This is why we can pour liquids, but we cannot pour solids. And then in a gas, the particles have even more freedom and even more space to move around. This is why a gas takes up much more space than a liquid. For example, if you were to take that glass of water and get it so hot that it became steam, you could fill an entire room with the steam. Because in a gas, the molecules are much farther apart and have much more energy and are moving much, much faster. Let's move on. You can see an illustration of this on slide 4. Let's see, the picture on the top right, you'll see 2 boxes with a lot of particles. Now that picture on the left, the particles are moving slower. so they have much shorter arrows. In the right, they're moving much faster, so they have much longer arrows. Right? So the temperature and the pressure would be higher on the right, over here. On slide 5, we can see how this motion of molecules affects the different states of matter. Let's start at the very bottom, in the solid phase. Now we know that when we're talking about water, we use the word ice to describe water in the solid phase. This is the phase where the molecules have very little energy, so there is very little motion. They are moving very slowly, and they are moving so slowly that they actually form a crystal. You can see in the picture down here next to solid phase, there are some lines between the different molecules. That represents the crystal structure of ice. That's why ice crystals have 6 sides. That's why snowflakes have 6 sides. Now, remember what we learned earlier about thermal energy. Those molecules in the ice crystal still have some thermal energy. They're just moving very small, they're moving a very small amount, and they're moving very, very slowly. Remember, they will not stop until we get down to absolute 0 degrees Kelvin. But let's move up the scale right now. We know that as we have increasing thermal energy and increasing temperature, the molecules will move faster and faster until the crystal breaks down and the ice melts into a liquid. So we would say the ice melts into water. The solid melts into a liquid. As our temperature increases, the molecules move faster and faster. They are farther apart until eventually they are unconstrained, and we go into the gas phase when molecules are moving much faster. That's like the steam coming out of a kettle on the oven. The gas phase of water, steam. So we would say the water evaporates into steam. All right. Now, let's say we keep getting hotter and hotter and hotter, like in a pressure cooker. Eventually, those water molecules will become so hot that the molecule itself will break down. Remember, we learned at the beginning of the lesson that a water molecule has 2 hydrogen atoms and 1 oxygen atom. Well, when the molecule becomes hot enough, the bond between the oxygen and the hydrogen will break, and the water molecule will break apart into 1 oxygen atom and 2 hydrogen atoms. So instead of water, you will have oxygen and hydrogen. This is how we know the different atoms that are in a water molecule. Now, we can still get even hotter. As we get even hotter, those atoms will start to break down, and we will start to enter the plasma phase. Now, perhaps you've learned a little bit about the structure of an atom, and we know we have that dense center called the nucleus, and in the nucleus we have two types of particles, protons and neutrons, and then moving around that nucleus we have much smaller particles called electrons. Well, as an atom gets hotter and hotter, the electrons will become more and more energized. So they will move into higher energy levels until eventually the nucleus will lose its hold on the electron, and the electrons will move freely. They will no longer be bound to the nucleus. That's what you see in the plasma phase right here. Free electrons move among positively charged ions because the hydrogen and oxygen atoms have lost their electrons. Let's move on. Temperature. Temperature measures the average kinetic energy of particles. Okay, let's talk about measurement very briefly. We know that if we want to measure mass, we measure mass with a scale. If we want to measure length, we measure length with a ruler. If we want to measure weight, we use a Newton spring scale. If we want to measure temperature, we use a thermometer. And that's the point you can see in C. We measure temperature with a thermometer. So how does a thermometer measure the kinetic energy of these particles, the kinetic energy of atoms and molecules? Well, let's move on to the next slide and take a look. Here we have a picture of 3 thermometers. We're looking at 3 different scales, but what I want you to think about first is the thermometer itself. The thermometer is made of glass. It's a long, thin glass tube, and inside we have that red liquid. Now that red liquid is mercury. Mercury is actually a metal. It's a very dense, very heavy metal. It's heavier than iron. It's heavier than gold. But mercury is very interesting because at room temperature, in a room like this, mercury is a liquid. Even though it's so heavy and so dense, it is still a liquid. Now what this means, remember we learned that when molecules become hotter and have more kinetic energy, there is more motion. So there's more motion as the particles move faster. They are farther apart. Think about the cars on a highway. When the cars are moving very slowly, they tend to be very close together. When cars are moving very quickly, they're going to be farther apart. Molecules are the same way. When they're moving faster, they're going to be farther apart. So what this means is that when matter becomes hot, the molecules are farther apart, so the matter expands. It becomes larger. That liquid mercury inside the thermometer, when it becomes hot, it expands, and it expands up the glass tube. So by measuring how far the mercury has expanded, we can measure the thermal energy in that mercury. And from that, we can determine the temperature. Now, the first man to realize this was a man named Celsius. And that's why his name is the name we use for that center scale, the Celsius scale. Celsius put mercury into a glass tube. He put it into a bucket of ice. The temperature dropped, and Celsius decided, hey, I'll call that point 0 degrees. The point where water freezes into ice, where water changes state. We'll call that 0. Then he put that same tube into boiling water, and the mercury expanded, and the mercury rose in the thermometer to this point. And he decided, hey, I'll call that 100 degrees Celsius. That makes things very easy to remember. 0 is the freezing point of water, 100 is the boiling point. If you look on the left, you'll see another scale called the Kelvin scale. Now you'll notice where Celsius goes from 0 to 100, Kelvin goes from 273.15 to 373.15. We'll notice that's the same interval. It's still a difference of 100 degrees. So a Celsius degree is the same as a Kelvin. It's just that the whole scale is moved down. Now, we're going to talk about why in a moment. If you notice on the right side, we have another scale called Fahrenheit. This is the scale that we use in my country, in the United States. It's a little bit different. In this scale, water freezes at 32 degrees, and it boils at 212. So you'll notice we have a difference there of 180. Now, so where Celsius has an interval of 100, we have an interval of 180. So you would have to multiply a Celsius degree by about 9/5 to get a Fahrenheit degree. A Celsius degree is much larger. So there's only 100 Celsius degrees, but there's 180 Fahrenheit degrees. So a Fahrenheit degree is much smaller. So, yeah. All right, let's move on. All right, okay. Let's go on and, now I told you we're going to talk about the Kelvin scale and why that 0 Kelvin is so much lower than 0 Celsius. Let's go into that now with heat. Heat energy. Okay. Heat is the transfer of thermal energy from one object to another because of a temperature difference. Okay. In this picture, we can see 3 types of transfer. We have a hand holding a pot over a fire. The first one I want to look at is that hand. you'll see the type of transfer there is conduction. Conduction. That's the transfer of heat because of touching. When sometimes you might touch a hot metal pot or a hot metal doorknob, and you'll notice you'll pull your hand away because it's so hot. That's what you're feeling there is conduction. It's heat energy from that hot pan or the hot doorknob being transferred to your hand. So transfer from touching. The next one, convection. You'll notice we have a lot of arrows in that pot, and they're kind of moving around like this. Now, why is this? Remember what we said. When matter becomes hot, the molecules they move faster, they're farther apart, so they're lighter. So particles with a lot of thermal energy that are moving very quickly are going to rise because they are lighter. You'll notice the arrows go around and around and around here. So the molecules go up, and I will highlight that. Down here at the bottom of the pot, the molecules start to move very quickly. That very hot water, the molecules are farther apart, so it's lighter. It rises to the top, it becomes cool, and it falls back down again. So we have this constant cycle that we call a convection current. That's why if you have a pot of boiling water, your hand is going to get hotter if you put your hand over the water than if you put your hand beside it. Try this sometime. Or if you have a fire, if you put your hand beside the fire, you feel a little bit of heat. But if you put your hand directly over the fire, it's going to become terribly hot. That's because when you're over the fire, you feel the heat from convection. But you don't feel that heat when you're beside the fire. The third type, down here, radiation. This is the transfer of heat not from touching and not from convection. But when you're beside a fire, you still feel some heat. That's heat from radiation. We're going to talk a little bit more about radiation in the coming slides. I do want to look at point B. Notice heat flows from higher temperature to lower temperature. This makes sense. Think about, imagine being at a party and one half of the room is very crowded and everyone's standing shoulder to shoulder, but the other half of the room, there are no people. What's going to happen? People are going to move from the crowded area to the empty area. Heat energy behaves the same way. We go from an area of very high energy to areas of very low energy. The energy will tend to balance and even out. So if one area is very high energy, one area is very low, heat is going to flow from areas of high temperature to areas of low temperature until we achieve a balance, a stasis. All right, let's move on. For thermal energy. Okay, the total potential and kinetic energy of a material depends on mass, temperature, and phase. Okay, so what that means is, well, tell you what, let's go to the next slide because there's a very good illustration. Here, Which beaker of water has more thermal energy? Notice, the first beaker, we have 200 milliliters of water at 80 degrees Celsius. In beaker B, we have 400 milliliters at 80 degrees Celsius. So we have the same temperature, but a different mass. That means that B has more thermal energy. Even though the temperature is the same, there's more mass, so there are more particles. So the particles in A and B, same temperature, they're going to be moving at the same speed. There's just a lot more of them in B. So B will have more thermal energy than A. All right, easy enough. Let's move on to the laws of thermodynamics. The first law, total energy does not change. All right, it can only change form. This is absolutely fundamental to our understanding of the universe. Let's take a few examples. If I have, say, a watch, the hands are moving around. Now, for that motion to occur, we have to have kinetic energy. Where is that energy coming from? Well, it comes from a battery. Now, if there's no battery, the watch will not run. We understand that, right? Well, that's because the battery has what we call chemical energy. And the watch, or any electrical appliance you use, like your cell phone or an MP3 player or a Nintendo DS, they're all going to convert chemical energy from the battery into electrical energy. So energy is not created, it only changes from chemical to electrical. From chemical to electrical, and then in the case of the watch, to kinetic energy. In the case of an MP3 player, to sound energy. And in the case of a video game, to light energy from the screen. All right. Maybe I can give you a few more examples there of the first law before we move on. Say a windmill. It catches the wind and turns a generator to make electricity. Well, that windmill converts mechanical energy into electrical energy. An iron that we use to iron our clothes, that converts electrical energy into heat energy. A light bulb converts electrical energy into light energy. Just a few examples, but the important thing to remember is we're not creating energy. We're only changing it. Second law. In the conversion of energy from one form to another, that means when we change from one to another, when the battery converts that chemical energy to electrical, when the iron converts electrical energy to heat, energy is lost. Yeah. Every step of the way, we lose a little bit of energy in the form of heat. Heat does not flow from cold bodies to hot bodies without adding energy to the system. And this is a concept we call entropy. The second law of thermodynamics. There cannot be a conversion of 100%. If you have that MP3 player or the cell phone, it cannot convert all of the chemical energy in the battery to light energy. I'll give you an example. I think most of you understand that when you have a laptop computer, If you have a battery in the laptop and you are using your computer, let's say you're on Facebook, you use it for an hour, you'll notice that the battery is very hot. That's an example of entropy. Your computer is designed to convert the chemical energy from the battery into light energy on the screen, and the energy, of course, to run the processor. But some of that energy will always be turned into heat. That's why your battery gets hot. It's the second law of thermodynamics, entropy. Entropy. All right, let's move on. Specific heat. All right. When we talk about specific heat, we're asking how much energy do we need? How much energy to raise 1 kilogram of some material 1 degree Kelvin? Now this is important because not all matter is the same. The amount of heat that you need, if you have 1 kilogram of water and 1 kilogram of iron, it will take a different amount of heat energy to raise the temperature 1 degree. We measure this in joules per kilogram Kelvin. We see here the formula. That means how much energy to raise the temperature of 1 kilogram 1 degree Kelvin. Joules per kilogram Kelvin. Now, let's look at an example. On slide 16, we have a 50-gram block of aluminum and a 50-gram block of copper, and it asks which sample will take longer to heat to 100 degrees Celsius. Which metal will require more energy? Well, let's look at our specific heat. Notice the specific heat of aluminum, 920 joules per kilogram per Kelvin. Copper, 380 joules per kilogram Kelvin. So aluminum requires much more energy to raise the temperature 1 degree Kelvin. So here, 920 joules per kilogram per Kelvin. Yeah. So aluminum requires much more energy. It has a higher specific heat. So you look down at the bottom. Aluminum has a high specific heat. It will require more energy to raise the temperature 1 degree Kelvin. Copper has a relatively low specific heat. So we say that copper is a good conductor of heat. It conducts heat very well. It only requires a small amount of heat, 380 joules, to raise 1 kilogram 1 degree Kelvin. Now, copper is a good conductor of heat. It is also a good conductor of electricity. That's why we use it for electronics. That's why we make electrical wires and cables out of copper, because it conducts electricity very well. It would be nice. Of course, it also conducts heat very well, so it means that the copper wire will get very hot. It will conduct electricity, but it also conducts heat and becomes hot. It would be nice if we could have a metal that conducted electricity very well, but did not conduct heat very well. Fortunately, we don't have anything like that. All right, so aluminum has a higher specific heat. It will take longer to cool down. Notice water has a very, very high specific heat. So it requires much more energy to heat 1 kilogram of water. All right. Okay. Let's review. Heat transfer. We saw this earlier with the pot of water. Conduction, that's direct contact. Contact means touching. Just like your hand, so when your hand is touching that hot pot, your hand feels hot. That's transfer by conduction. Solids do it best. Each material has a different ability. That's the specific heat. All right, convection. Fluid motion is required. Remember, fluid motion, the movement of particles, just like those water molecules moving around in the pot. At the bottom, they become hot. They have more kinetic energy. They move faster. They're farther apart. They're lighter. They rise to the top. They cool down. They move slower. They're closer together. They're heavier. They fall. And again, hotter, colder, hotter, colder. Always moving around and around. Convection. That's when you place your heat over the flame and your hand feels very, very hot. That's transfer by convection. Next, radiation. No medium is required. Even if there are no molecules, there's no water molecules, there's no air molecules, we can still have radiation because radiation is transferred by waves. This is how the sun heats Earth, how that heat energy from the sun comes to Earth. Remember, there's no air in outer space. There's no medium to carry that energy. So we have, it's transferred by waves, the waves of photons. And some examples would be light, ultraviolet light or UV, and microwaves. All of these come to Earth from the sun. Okie dokie. Okay, so we know materials on slide 21. We know that materials absorb heat energy at different rates. Dark materials absorb more light, absorb more heat energy, and light materials reflect more. This is why if it's hot outside and you're wearing a dark shirt, like a black shirt, you're going to get very hot. But if you're wearing a white shirt, you stay nice and cool, because that dark material will absorb more heat energy, and the light or white material will reflect more heat energy. We also know that rough materials absorb more heat energy, but smooth materials reflect it. A good example is a mirror or a pane of glass. The glass is very smooth, so it reflects more light. Okay. Conductors. We've talked about conductors already. These are the materials that allow energy to flow easily through. Okay? For example, copper is a good conductor. Silver is a good conductor. Gold is a very good conductor. And that is why those materials, if we go back to page 16, you'll see those good conductors have a very low specific heat. They conduct heat well, so you only need a little bit of heat to raise the temperature. All right? With that, we'll go ahead and finish. That's the end of our slideshow. I hope you enjoyed it. I hope you found it informative, and I hope to see you again next time. Bye. Right. All right. Alrighty then.
Yeah, we'll try to have more slides sent to you ahead of time.
Cool. That was fun. I probably got to be running along to
Sure.
Bang Clear Bang Rong.